Hello, Chem 112. It's Virginia here, and we're going to talk about buffers and titrations. This worksheet is posted on the ebook in the handouts and materials page if you want to find that and go along. And I did add some problems in here that aren't on that original worksheet, so make sure you pause it, look at what I've added in, and try to work it out for yourself also. Okay, here we go. So, we have different types of solutions that we work with in Chem 112. We have our strong acids or bases, our weak acids or bases, we have our buffer solutions, and then we have the situation of titrations, where we start mixing together acids and bases and neutralizing them. And so, being able to recognize what sorts of solutions we start with and what we're mixing together is going to make a really big impact on solving these problems. Okay, so in this first situation, we have strong acids and bases. And so these solutions completely dissociate, and so they're not we can kind of treat them like salts, where they're going to completely dissipate into H plus and Cl minus in this case, or calcium ions into hydroxide ions. And so to be able to find the pH or pOH from these solutions, we can just use traditional stoichiometry to solve those problems. However, when we have something that's weak, we know now they're not completely dissociating and we're at equilibrium. And so in order to figure out the pH of these solutions, we have to use an ice table and our equilibrium expression. So in this example where we have ammonia, we're going to start by writing a base hydrolysis reaction. We've practiced our classification. We know that ammonia is a weak base and that it will take a proton from water and generate hydroxides in solution. And because this is a base reaction, we need a Kb, which they've given us, and we know that our Kb expression is going to be equal to our aqueous products over our aqueous reactants. So we'll have the ammonium times hydroxide divided by the ammonia concentration. And that's equal to the 1.8 times 10 to the minus 5. And so to start our ice table, we can plug in our initial concentration for ammonia. In ice tables, we use molarity, so we actually don't need to use that volume that was provided. Ice tables and equilibrium are all done with concentrations rather than moles. We'll use the moles with our ICF tables. So to start, I have 2 molar ammonia. I'm not going to keep track of water. It's a liquid. It's not going to be part of our equilibrium. And we'll have 0 of our products to start. And so I'm going to add to that side. So those will both have plus X added. And we'll lose X from the ammonia side. For our equilibrium row, we're just going to combine our 2 IC rows. Okay. And then once we have those expressions, we are going to plug it into our Kb and solve for X. So this is how we'll start. And the reason that the denominator is just written as 2 there is because our Kb is small enough, it's 10 to the minus 5 or smaller, that we can ignore any added or subtracted x's. So we'll have x squared divided by 2 equal to our Kb. And to solve this is easy. We're just going to multiply our Kb by 2 and then take the square root. And that will give us an X of 0.006. And if we look at our table, we know that X is going to be equal to our hydroxide concentration. So when we go ahead and take the negative log of this, we'll end up with pOH. And it ends up equaling 2.22. But that's not the answer we're going to choose. We want pH, so we're going to have to use our relationship with pKw and say 14 minus pOH is equal to pH. And we know we started with a weak base, so it makes sense that our pH should end up being greater than 7. So that checks out. So now we can think about making buffers. The key to a buffer is having either a weak acid or weak base present with its conjugate. So you need to have both the weak thing and its conjugate in similar amounts. Doesn't have to be exactly the same, just similar. And I personally like finding when we have a buffer solution because it means we can skip doing an ice table and we can use the Henderson-Hasselbalch equation. And this is going to be on the data sheet, but it is for each case going to be pH equals pKa plus the log of base over acid. And one thing that's nice here too is because we have this ratio of base over acid, it doesn't matter what units we use as long as we plug them in so that the base units and the acid units are the same. And so what ends up happening with a buffer is if we add in some acid, it's going to react with whatever conjugate base is there to reform the conjugate acid. And if we add in some base, it's going to react with the conjugate acid to make some conjugate base. And so we sort of have a sponge for either acid or base that's added in. And so it's going to resist changes in pH. And this is really important in lots of different applications. Most commonly thought about is in the body. Because if you're exercising a lot, generating CO2, lactic acid, whatever, you don't want that to change the pH around your muscles, or else that could cause other problems. And so your body is buffering that to keep everything at homeostasis. So let's go ahead and see an example of a buffer solution. Here we say, what is the pH of a buffer solution made by mixing 100 mils of 0.2 molar acetic acid with 200 mils of 0.15 molar potassium acetate? And we're given the Ka of acetic acid. So we know that a conjugate pair is going to just differ by one proton, and we can write that with the equilibrium for acetic acid. So we have that reaction here. And we can go ahead and see how many moles of each of these we have. And the reason we want to use moles is because we have different volumes. So we can't just simply add together the concentrations or just keep everything in concentrations. We'll have to do this in terms of moles. And so to get moles, we're going to do liters times our molarity. So for the acetic acid, we'll have 0.1 times 0.2, and so we'll have 0.02 moles. And if I want to figure out the moles of the acetate ion, I have to think about how this potassium acetate will dissociate. And so it's a salt, so it's going to completely dissociate in water, and we'll end up with our acetate ion and potassium ions, which are spectators. So we can disregard those. And so the moles of potassium acetate should be equal to our moles of just acetate. So we can go ahead and do the liters times that concentration, and we'll end up with 0.03 moles of that. And we're starting with 0 protons. And we eventually want to figure out pH, so we do care about what this proton amount ends up being. But it's nice because I see I have conjugate acid, I have conjugate base, so I can go ahead and use the Henderson-Hasselbalch equation and just directly plug in those values that I've solved for. So we're going to have pH equal to pKa plus the log of base. So we're going to have our acetate amount. So 0.03 divided by our acid amount, 0.02. And so this is going to be equal to the negative log of our Ka to get pKa. Plus that log. And we can punch this in and see that our pH will end up being 4.93.